Hey guys, I'm going to teach you about logistic growth equations. We're going to be converting differential equations into a solution using an initial condition. And you might notice it's a little bit darker. I'm going to try and see if we can get rid of that buzzing sound if the lights are off. If that doesn't work, then we'll turn the lights back on next time. Okay, so this is 6.5 logistic equations. So we've talked about exponential growth, okay? We've done the y equals CE to the KT. But what you notice about when I put this in a real life situation is that typically it's not going to be unlimited growth. It's not just going to keep going forever and ever and ever to infinity. Typically, something will level off when we're representing real life situations, okay? Especially with population growth. Typically, you're going to come up with you're going to hit a maximum population, and then the population will kind of hang out there or decrease from there. And lots of different reasons why. That people die, people get old, people don't keep having kids, and so it will kind of equal each other out and it levels off. So that's how we're going to call it a logistic equation, because it will show that leveling off that we're talking about, okay? So the equation for a logistic growth or decay is going to be dP dt equals Kp times m minus p. So you'll need to memorize that. You'll need to know where each letter goes and what each letter stands for, okay? So the m is the carrying capacity, okay? So m is the carrying capacity. And what the carrying capacity represents is, if you think about something that levels off, it's a horizontal asymptote. Okay, so the m value is a horizontal asymptote. So if it tells me the maximum number of population, what it could be, then that's going to be my horizontal asymptote, or my limit as t approaches infinity, or as time gets extremely large, okay? So the solution of this, so if I go through and solve this, which we are going to do, is this, okay? You only have to go through and solve that one time with me in notes, and then I think one time in homework. Otherwise, if you know where each of these letters will move, you can manipulate the equation around and plug in the values instead of going through and solving the differential equation, okay? Be very careful that you do not call this C the initial amount. Underline, star, highlight it. I guarantee you will have a test question that will ask you for the initial amount, and it's pretty tempting to use that number that's right there, but it is not it on a multiple choice question, okay? Let's go through an example of how this logistic equation would work. So we're talking about a national park, and we're talking about grizzly bears. It's capable of supporting no more than 100 grizzly bears. So right there, this is my carrying capacity. And that letter is M. So M equals 100, okay? We model the equation with a logistic differential equation where K is 0.001. Write the differential equation. So I'm going to write dP dt. It's a differential equation, which means it's going to have the derivative, right? K is the first number, that's going to be 0.001 times P is my variable. M is the carrying capacity, which is 100, minus P, right? So that's the first thing you need to know how to do, is to take information that they give you and put it into the positions that it would go in the equation, all right? Now it says the slope field is shown. Where does there appear to be a horizontal asymptote? Well, I kind of already gave you this away. But if I look over here at this equation, if it comes down this way, it's leveling off here. And if it comes up this way, it's leveling off here. So there's going to be a horizontal asymptote right here in the middle, which is at 100. Okay. So it says, where does it look like it's going to be a horizontal asymptote? It's going to be at P equals 100. Okay, what happens if the starting point is above the asymptote? So if I started up here on my starting point, then my graph's going to kind of go down like this, and then it's going to approach the asymptote, right? So if I am starting up high, then the population is going to decrease. So the population will decrease toward 100. All right, well, what happens if the initial point is down here? Then it's going to start at that population, and the population is just going to grow from there. Okay, so it's going to grow if it starts below the asymptote or the carrying capacity. So the population will increase toward 100. So see, we can still have growth and decay, but it is going to reach a certain point. Okay, so this says if the park starts with 10 bears, so that means at 0, there's 10 bears. Then I'm going to start right here. This one's 20, so let's say 10 is about right here. Okay, this is where we start at 0. If I follow the curve here, this is going to go like this. Remember, we keep the slope in between. Okay, and then notice that this is going to kind of start to level off a little bit up until we get to here. So logistic growth model is going to kind of go slow for a minute, and then it will look like this. Okay, so if the carrying capacity is 100, then at 50, something's going to happen. Okay, so you always want to look at the carrying capacity divided by half is when the population is going to have the steepest curve. Okay, at half the carrying capacity. We'll go over that on the next slide. So we figured out how to write the equation and to interpret what it would mean depending on where the populations start, and then what the slope field will look like, or what a logistic growth model looks like. Okay, so in part D, we're going to solve the differential equation to find P of T with the initial condition of 0, 10. Okay, so I'm actually going to do this on a separate paper because this takes quite a bit of space, and I don't want to squish it. I want you guys to understand what we're doing. Okay, so we're going to start off by writing the equation that we wrote already. Okay, so I'm going to solve this differential equation for P. So I have to separate the variables. Okay, so I'm going to multiply dt up here, but then I would have to take my p's to the other side by dividing. So 1 over p times 100 minus p dp equals 0.001 dt. Okay, so that's our first step, is to separate the variables. Now, next step I would be to take the integral of these, right? To solve for p. How do I take the integral of p times 100 minus p? Hopefully you're thinking this is partial fraction, okay? So a over p plus b over 100 minus p equals 1 over p times 100 minus p. Okay, we need to go through the process using our partial fraction to solve this. So a is going to multiply by 100 minus p. B is going to multiply by p, and that will equal 1. Okay, so I'm going to let p equal 100. So if P is 100 here, then this cancels out. This would be 100 times B equals 1. So B equals 1 over 100. Let's do the same thing for the other one and let it equal 0 so that this one will cancel out. So if I put a 0 here, I now have 100A equals 1, and A equals 1 over 100. Okay, so we know what A and B are. So I can go back into my integral, and I can write that as A is 1 over 100 divided by P plus 1 over 100 divided by 100 minus P. Okay, so far we have separated the variables. We've taken the integral, and to do that we had to do partial fractions. And now we're going to take the integral. Okay, so the integral of 1 over 100 times P is going to be, I'm not going to put an equal sign because there's one in the equation. It's going to be 1 over 100 times the natural log of P. And then this one is going to be 1 over 100 times the natural log of 100 minus P. But remember, I have this negative P inside. And so I have to put that times -1, or it's an integral. So we'd actually divide by -1, but where it's a 1, I just put times. And then that equals 0.001 T plus C. Okay, so we've taken the integral. Now what I want to do is I need to take this equation and you need to solve for P and manipulate it so that I can get it in the form that we just learned. Okay, you want to get it in that form that we just learned where it said P equals. I'm going to write this right here so you can see the form that we want to get it into. Now this one is a negative, so don't lose that negative sign. Okay, so this is what we're going for. P equals. So I'm looking at this, and I've got to get this to look like that. So let's just start simplifying. Let's first get rid of the 100. So this is going to be the natural log of P plus or minus the natural log of 100 minus P. And then that equals 0.1 T plus C. Multiplied by 100. So technically it's a new C, but that doesn't really matter. We're going to finish solving that. Okay, I can combine my natural logs by dividing, but it's going to be a lot easier to have just the P in the bottom. So I'm going to switch this negative around. And the other reason you can look and you can see is that when I solve for this, I'm going to have a negative. Sorry about that, a negative in for my T. So we want this to be a negative as well to manipulate that. So I'm just going to switch this to a negative, this to a positive, and this to a negative. Okay, now I can change my natural log around so that this is divided by this as one natural log. All right, so now I need to get the ln. To get rid of ln, I do e to both sides. When I have an e and an ln, it crosses off. So this is just going to be 100 minus p divided by p. This is going to be e to this times e to this. Okay, so remember, when I add like this, it's the same as multiplying because we add those two together to get this. Okay, so what that means is this term, e to the c2, that's just a c value that's multiplied by this. Okay, so this is going to be 100 minus p divided by p equals C3 e to the negative 0.1 t. Okay, now I need to multiply this by p. So then I have 100 minus p equals c e to the negative 0.1 t times p. Okay, and then what we're going to do here is we want to simplify it so that we can get the p's together, right? So instead of doing this, what else could we do to simplify this together? Because I can't get these p's together like this, right? So this isn't going to work. So instead, why don't we try to separate these? So I get 100 over p minus p over p, which is 1. And that makes more sense because we want to have that p by itself, okay? So then I have 100 equals C3e negative 0.1 t plus 1. Okay, and then if I multiply by p and then divide, then I'm going to get 100 divided by 1 plus c e to the negative 0.1 t equals p. Okay, when you get to this step, you're going to do the 100 over p and then the negative p over p. All right, now we have an initial condition of 0, 10. So plug in a 0 here, and e to the 0 is 1. So this will just turn into 1 plus c. And p is 10. Divide by 10. And subtract 1. I did it too fast in my head. 100 divided by 10 is 10, and then 10 minus 1 is 9. So c equals 9. Going back to our formula right here, p equals 100 divided by 1 plus 9 e to the negative 0.1 t. And we're done. From here, you could find your carrying capacity is 100. Right? Now, the other way that we could solve this, okay, instead is by using the formula that we know, okay, and we knew the differential equation. Okay, so I know m is 100, and I know k is 0.001. So using this equation, if I have this one memorized, I can just go straight to here. P equals 100 divided by 1 plus c e to the negative 0.001 times 100 times t. Okay, and then we end up with the same equation, 100 over 1 plus c e to the negative 0.1 t. We end up with the same equation that we came up with, and then we use our initial condition of 0, 10, and we get p equals 100 divided by 1 plus 9 e to negative 0.1 t. So this is what you can do from now on. When it gives you this, you can put it right into this equation and not have to go through all the stuff that we just did, unless it specifically says to show the work, which there is one problem that asks for that. Okay. All right. Then this says find the limit as t approaches infinity. This is asking for the horizontal asymptote, right? So what is the horizontal asymptote of the equation? What's the carrying capacity? It's 100. Okay. So the limit as that happens is 100. When will the bear population reach 50? Well, set this equal to 50. Set it equal to 50 and then solve. Okay, I'm just going to use the calculator for that. Okay, so I'm going to put 50, and then I'm going to put 100 divided by. Okay, so I have my two equations, and I want to find where they cross. And remember, the x value in this is talking about time. So you probably want to change your x max to 100. 100 years is a pretty long time. And then you know that the y max is 100. So I usually go a little bit higher than it so I can see the whole thing. Okay, so there's your curve. And I want to find out where that crosses the 50. So then I'm going to go still graphing. I actually went pretty high. Probably going to take a little bit too long. Let's do 110 instead. Okay, so second trace, where do those intersect? And we get 21.972. So T equals 21.972. And then if we go back to our original problem, this is telling us grizzly bears and T is in years, right? So 21.972 years. Okay, and then H says, when is the bear population growing the fastest? So remember, the steepest slope is at half carrying capacity. Okay, so it's growing the fastest when T equals 50, or when the population is half of the carrying capacity. So when the population is 50, it's going to grow the fastest, and they already know that that's 21.972 because we just solved for that. Okay. All right, so that's all the notes is just using this logistic growth equation to analyze these functions and then plug them in and solve. Okay, I'll talk to you later.